So from last video, we saw the LP space is a vector space. Basically, it's one of the consequences in the proof of the Minkowski's inequality. And we also have a semi-norm on this vector space. So based on the standard trick we saw earlier in this course, we can now construct a normed vector space by quotienting out where the semi-norm is equal to 0. Okay, so for the LP space, so let's define the N to be the kernel of the semi-norm, basically all the F where the semi-norm is equal to 0. When the semi-norm is equal to 0 is essentially saying F is 0 almost everywhere because you're integrating some function and you integrate it to 0, so this function has to be 0 almost everywhere. It's fairly simple to see that. And you define the curly LP, so this curly LP space is just the quotient of the LP space, the capital LP, over this kernel, so you quotient out the kernel, and you will get a vector space, a normed vector space, where the norm is given by the equivalence class of F. You just pick anything inside this equivalence class and you assign the P norm to be the P norm of this F. Okay, this is well defined. We kind of proved it earlier when you talk about the quotient of a semi-norm. So we do have a LP space with this P norm as a normed vector space. Usually when we talk about the curly LP, we just kind of ignore the plus n part. It's just sometimes abuse our notation. So we kind of remove this plus n part and just say the P norm is just the usual P norm you expect, okay? And similarly, you can do something similar for the L infinity space, okay? So I'm going to put this on your assignment, but the idea is the same, okay? You have a semi-norm on the L infinity space, so you quotient out the kernel, you get a normal vector space, okay? So that's all good. And in this video, I'm just going to show the LP space is not only a normal vector space, but it's actually also complete, okay? Remember, we proved the L1 space is complete. Okay, now we're just proving the LP space is complete. And following a very similar technique, you can prove the L infinity space is also complete. So they're all Banach space, okay? They're all complete normed vector space, okay? So they're all Banach space. All right, so the main theorem of this video is to show this curly LP is complete, okay? So the proof is really similar to how we prove the L1 space is complete, okay? So if you recall, because we have a normed vector space, so usually we just need to prove every Cauchy sequence has a convergent subsequence. And a standard trick says you can just by dropping, because if you have a subsequence of a Cauchy sequence converge, then the entire Cauchy sequence converge, so you drop to the subsequence, you can control the norm or the distance between the two values, okay? And then you can just might as well just assume they are the distance, because you are in a vector space, you take their difference, you basically show that if you have a bunch of things and norm is controlled by a summable sequence, then this entire sequence is summable, okay? So that's kind of the idea back then when we proved the L1 is complete, okay? So essentially, without loss of generality, let's take a sequence, let's say Fn, inside the LP space, okay? So here I'm no longer writing Fn plus the kernel, okay? Let's just pretend they're functions or equivalence class of functions. Okay, so let's take Fn inside this LP space, and we can assume the norm of Fn is controlled by some summable sequence, so might as well just assume 2 to the negative n, okay? And I need to show the following. So if you recall what we did when we proved the L1 is complete, we just need to show that the summation of these Fn when n going from 1 to infinity, that actually exists, okay? So in other words, this is essentially the limit as k goes to infinity of the k's partial sum, and going from 1 to k of these Fn, okay? That exists. Not only exists, but actually we want to show that it exists in LP and the convergence is in LP, okay? So it exists in LP and this converge inside LP norm, okay, in the right sense, basically, okay? So there are many ways of convergence. We're not only saying the pointwise convergence, but also the P norm convergence, okay? So we similar to what we did before, let's call this big F of k, the kth partial sum. And then let's do something similar for the absolute value. So let's say the h sub k to be the kth partial sum of the absolute value of these fn, okay? And one thing we know is that the h norm by the Minkowski's inequality, this h, the p norm of this h is bounded above by the sum of the p norm of these f. Okay, so everything is this is less than equal to the negative n, so this sum is less than equal to 1. Okay, so you have something less than equal to 1. And so because these hk is non-negative and they're increasing, you're adding some non-negative function one at a time, so they have to converge. Okay, so the h is equals to the limit, the pointwise limit of these hk, okay, or essentially just the sum of all the absolute value of fn, okay? So this h, because it's a pointwise limit of a bunch of non-negative things, so by the MCT, you have the, technically you do the hk to the power p, but you have the p norm of this h is also the limit of the p norm of these hk, so it's less than equal to 1, okay? So in other words, h itself is inside LP as well, okay? So this is inside LP, okay? So because it's inside LP, so the integral of h raised to the power p is less than infinity. So in particular, this h of x is going to be less than infinity almost everywhere, okay? For almost all the x, if you take the sum of the absolute value of the fn of x, you get something that's finite, okay? In other words, the sequence fn of x will converge absolutely. So this will imply whenever this is less than infinity, so this big f of x equals to the sum of all the fn of x here, and going from 1 to infinity, that one exists almost everywhere. Okay, that's just because when a series is convergent absolutely, then the series itself must converge. Okay, so we get this f. Okay, so this f is basically a pointwise limit of the partial sums. Okay, so this is pointwise limit. Okay, so pointwise. All right, so we have a pointwise limit, and one thing is fairly clear is when you do the sum of a bunch of, actually I should say that if the series doesn't exist, I just let f of x equal to 0 if the summation fn of x do not exist. Okay, so it's on a measure 0 set, so we really don't care about that. And when it exists, then clearly I have the absolute value of f is going to be bounded above by when you put absolute value on each of these fn, so it's going to be less than equals to h for sure. Okay, and similarly, you will have each of these fn, if you consider minus f, okay, they're also bounded above by this h as well. Okay, so to the absolute value, this is basically the tail is bounded above by h. Okay, so by the first one, the absolute value of f bounded above by h, then automatically you know that this f has to be in LP. Okay, so this is in LP. I should use the curly LP of mu. Okay, this is just because when you raise to the pth power, the pth power of f is dominated by pth power of h, and h is in LP, so you have something in LP. And the second one, because each of these is bounded above by this h, and also you have something more, so the difference is converging to 0 almost everywhere. Okay, so if you raise the power to the p, so fn minus f raised to the power p d mu, well, this one is pointwise converged to 0, and you have something that's inside LP, or raised to the power p is inside L1. Okay, so by the dominantly convergence, so LDCT tells you this one will converge to 0. Okay, so this is simply the p norm of fn minus f. Okay, so the difference in the p norm is going to 0. Okay, so basically this shows the sequence converge. This Cauchy sequence fn converges. Okay, it converges to the limit as you expected. and that basically shows the LP space is complete. Okay, if you compare this proof with how we prove L1 is complete, they're essentially the same proof.